I'm Alessandro Campanella. I'm from Italy. I'm working on communications since 2003 approximately, and I'd like to call myself as a MikroTik evangelist. I'm a consultant and a trainer. And I was here during the first MikroTik user meeting in 2006. This is my T-shirt of the event, and this is my training class. As you can see, we have some very important people here. Arnis, the CTO of MikroTik, Yanis on the right, Maya, maybe someone of you knows him, and Tom and Patrick, who was in my class, so they gave the presentation before me. And I'm in the middle there. So today I want to talk about ISP data center made with MikroTik. When I started doing this job, MikroTik wasn't exactly the right solution. The first name that came to mind when someone need to build a data center architecture, especially for scalability, redundancy, performance. Of course, MikroTik evolved very rapidly in the last years, and now we have some very smart solution to offer. And we saw MikroTik evolving from basic routing to layer 3 hardware offloading, from STP-based layer 2 solution to MLAG setups, and from simple VLANs, segmentation, to ISP-grade network architectures. So I think MikroTik is no longer an affordable alternative to other vendors, but can be a key enabler for ISP data center. Of course, this is my personal approach. I want to consider this presentation as a point, a starting point for a discussion, maybe, but it's a result of my own experience. And I think a well-designed MikroTik architecture can be very interesting, but you have to know how to use the full potential of MikroTik, of course. So let's have a look at the topology I want to present today. This diagram summarize all the components of a data center. Starting from the left, we have the peering, so the upstream providers, the BGP routers, the MLAG solution, I think is the core of the data center, some access concentrator, let's say, and wholesale kits, routers or firewall that I put in the middle between the public part of the network and the local private part of the network, when we can have another MLAG switch and some servers, applications, and whatever we need to put inside the data center. So the MLAG. First of all, the MLAG. The MLAG is mandatory, in my opinion, to ensure redundancy without sacrificing performance. If a core switch fails, of course, it's a very big problem, and MLAG can handle this problem. To create a multiple chassis link, we can change the game in a sense, because we don't have blocking links, so all the links are active at the same time. We have instant failover, bad load balancing, and I think seamless scalability. I mean, if you need to add another device to the network, you don't need to reconfigure everything. You just plug it and tag your VLANs and so on. Multiple chassis link aggregation group, MLAG, allows to create a structure in which two separate switches function as a single switch. So in case you have some problem with one switch, or you need to upgrade the software of one switch, the other is working at the same time. And all the links remain active during this process. The traffic is going on all the links at the same time. To do an MLAG configuration, we need two cloud router switch series 3 or 5, or 2000 series cloud core routers, of course. So the new Prestera Marvel chips. We need a dedicated peer port in which the switches will run inter-chassis protocol, control protocol, ICCP, and they share MAC tables, systems information, and so on. MLAG requires spanning tree protocol, rapid spanning tree protocol, or better, multiple spanning tree protocol. We show you in a later slide why multiple spanning tree protocol is so important in this configuration. We need a dedicated untagged VLAN to pass all this information between the two switches, and we can use a bounding interface to connect the two switches. This is very important too, because in case the connection between the two switches fails, it's a big problem for MLAG. So using a bonding interface is a very good practice. By the way, the MLAG is not compatible with layer 3 hardware offloading, but only on switches. So we can use the MLAG for the switches and layer 3 hardware offloading in the rest of the network, and I will show you how. This is the configuration, simple configuration of an MLAG. So the two switches are configured as in this simple code configuration. Please note that the router over there is using a normal AD bonding interface with two slaves interface, and the router will see all the interfaces as active. So it will use both the interface at the same time. We have a target VLAN in the router and an untagged VLAN, the 4000, let's say, it's an example, to let the switches communicate one each other through the ICCP port. All the screenshots I insert in the presentation are belongs to real life scenarios. So these are two CRS 520 switches, great machines, configured as an MLAG. And as you can see, we have the VLAN 1 tagged on the ICCP port, as well as all the VLANs tagged in the same port. And the routers the switches are acting as an MLAG. The CPU load is quite approximately 0. Do you know that we can configure an MLAG with another MLAG? So we can configure an MLAG in this square topology in which a couple of MLAG switches can connect to another couple of MLAG switches, and each couple of switches believes that they are communicating with just one switch. So we can have this topology, and it's very good in data center. We can also use a bounding interface to connect the two switches, and starting from 7.17 router OS version, also the active backup supports hardware offloadings. What does it mean? That we can do something like this. We can connect two data centers together with a couple of 100 gigabit interface, still having a backup port in the 25 gigabit port. So we can have the ICCP connection with two different speeds in hardware offloading. It's a very nice configuration. We have 200 gigabits from the left to the right. So we have the underlay, now we need the overlay. We do it with VLANs. VLANs is very important. It's crucial to ensure communication between devices. MLAG allows VLANs to be distributed across all the switches and to all devices. And we need to create some VLAN maps inside the topology and the diagram I showed you before. We need to configure both. MLAG switches with the VLANs. This is a diagram showing the VLANs I create usually, one for IBGP connection between the two BGP routers, and four for the connection of the access concentrator with both the IBGP routers and from the routers to the IBGP connection. I mean, it's just an example, but it's what I configure usually. So we have, in this example, two BGP routers, three access concentrator, two firewalls, routers, what else? And we want to grant efficient routing, redundancy, and security. IBGP is used to synchronize the routing tables of the two BGP switches, of course, and they act as a route reflector for the entire network. So the IBGP is set up between the two routers through the switches. In this case, we will see later another example, and they establish both IPv4 and IPv6 IBGP peering. Then we need the VLANs from the BGP's routers to the other devices, access concentrators and firewalls, and we do not want to establish a full mesh IBGP connection, so we use these two BGP routers as a route reflector, and I use OSPF usually only to for the distribution of the loopback IP of the devices. Then I use BGP to share the default route to all these devices and to obtain all the prefixes I need to share and distribute all over the network. Also, this is a configuration of the peering part of the network. Here we have the upstream provider. I prefer to connect to the MLAG switches, the upstream provider, and I configure the switches as an edge port because I don't want to extend my spanning tree protocol network or to other actors. And I use in VLAN ingress filtering, admitting only untagged traffic in this case. Okay, so, and the VLAN is tagged on the ICCP interface at the same time. In case our upstream provider can provide us with link aggregation, so two different interfaces, we can use MLAG this way. Otherwise, if they provide us only one interface, a single interface, we can decide to connect one provider to a switch and one upstream provider to another switch, just to balance the traffic and to prevent some single point of failure. I prefer to define as an edge port the switch port, not to extend my SDP to others. And in case we don't want to gather some BPDUs packets, we can set up the BPDU guard on the interface, just in case we need. Ingress filtering is enabled, and we want only untagged traffic in this case to come inside the network. So even in this case, we don't want to share our VLANs to the other providers. This is the other part of the network in which we have the wholesale provider. They will give us the customers inside their VLANs, the customer VLAN and the service VLAN usually, and we need to take these VLANs to these customers to the access concentrator. In this case, I suggest to connect to the MLAG the same, but in this case, the port is still an edge port, but I use tag stacking. So tag stacking is a technology in which we can leave the VLANs as they are and insert inside, encapsulate inside another VLAN and transport all these VLANs to the access concentrators. In this case, I use admit only tagged because I don't want untagged traffic to go through these MLAG ports. This configuration can be done in Q-in-Q configuration or in double Q VLAN. So, you know, we have two different kind of protocols, header type, so we can use both. And tag stacking is working the same with both VLANs type. Recently, in 7.17, MikroTik released the new PPPoE server capability that can operate directly on VLAN. So we don't need to define each customer VLAN on the service VLAN. The PPPoE server can work in a VLAN range from, let's say, 1,000 to 3,099. And in this case, we don't need to configure each single customer VLAN, bridge them together, or put a PPPoE server on each customer VLANs. No more. And this is the main part of the presentation, layer 3 hardware offloading. Of course, to run layer 3 hardware offloading really changed the game. It delegates routing to the chipset and not to the CPU itself. And it significantly boosts network performance, increasing throughput, reducing latency, optimizing CPU utilization, and improving scalability. Even with this feature, we need specific switch chips, such as the one we can find in Cloud Router Switch 3 and 5 series and 2000 Cloud Core routers. But some functionalities, MLAG, VRF, VRRP are not compatible. So can still we use layer 3 hardware offloading in this topology? Spoiler alert, yes, of course. Let's say how. First of all, a little tip. When I imagine devices, I prefer to imagine them as composed by two different parts, the switch and the router mixed together in a single chassis. So it helps me to understand where to tag VLANs, what to put in a bridge, and so on, especially for layer 3 hardware offloading purpose. So we have a switch, we have a router, it's the same device, but imagine we have two different devices. In this case, we can put the bounding interface going to the MLAG in a bridge without any other interface. So we create a bridge, we add the MLAG interface in the bridge, and we can then activate VLAN filtering on the bridge, tag the VLANs we want to put in hardware offloading both on the bounding interface and on the bridge to let the router receive this VLAN, define VLAN interface in interface VLAN, and enable layer 3 hardware offloading, and the game is done. Even this, this screenshot is the only simulated one. We have two routers running hardware offloading. The difference is that without hardware offloading, we have 16% of CPU load and 0.5% of CPU load with the same traffic, 10 gigabits approximately in this simulation. This is the configuration for the BGP. So each upstream provider can have its own VLAN. We can configure these VLANs on both the BGP routers, and we can use hardware offloading, layer 3 hardware offloading, both on IPv4 and IPv6. And what about connecting the two BGP routers together? So if we want to establish a iBGP connection between the two routers directly connected, we cannot use a simple configuration because the MLAG switch acts as a root bridge. So the traffic will flow through the switches. We need to configure multiple spanning tree protocol and create a new instance of the multiple spanning tree protocol dedicated to the VLAN that we want to pass through this direct connected interface. In this case, we can create a different priority for this instance and run the other priority for the other VLANs. In this case, we have a good load sharing between the direct connected interface and the other interfaces. What about VRRP? Well, VRRP is not compatible with layer 3 hardware offloading. It's a trick, of course. These slides is a trick. I used to configure IPv6 VRRP using link local addresses and set up the IPv4 address not in the VRRP interface on the master, but on the VLAN itself. And the other IP, the same IP, on the VRRP interface on the backup. In this way, when master is master, we have full hardware offloading of the IPv4. In case of a backup event, we will use the CPU. But in master configuration, we have the offloading of all the routing. Another slide, hardware offloading enable, a layer 3 hardware offloading enable, 1.5 million routes in the router. Please consider these numbers. We have 1 million routes in the routing table, 28,000 prefixes are offloaded, and the most important parameters is the IPv4 shortest hardware offloaded prefix. What does it mean? That the router is able to offload only the smaller prefixes and not the bigger. And we can assume that the smaller is the one that drive more traffic, port more traffic to the network. In this case, the 24 prefix is of course shorter than the /16. It contains less IPs, it means. And all the other prefixes are processed by the CPU. In case the IPv4 shortest hardware offloading prefix is 0, it means that everything, all the routes are in the hardware offloading. Otherwise, only the smaller one. Of course, it depends on the model. Cloud Core Router 2216 is able to offload up to 120,000 prefixes in IPv4, and the 2116 only 36,000. It depends on the network and on what we want to do. However, if we analyze the traffic, we can raise top traffic generating autonomous systems, in which we decide which autonomous system is the one to put in the hardware offloading and one is not. So in this case, we can use, for example, routing filters to enable and disable hardware offloading for these autonomous systems. And for example, we can decide that the prefixes belonging to our network are hardware offloaded, even if the network is bigger than 24, and decide what to do for the remaining prefixes. Real-life configuration, 41 active BGP peers, layer 3 hardware offloading enable, disable, the CPU load is absolutely evident. So 0.8 with layer 3 hardware offloading enable, and layer 3 hardware offloading disable is up to 4 approximately %. And what about VRF? Is not compatible at all, unfortunately. But we can use the VRF still to configure the management interface. So we can set up a different VRF for the management interface and dedicating SSH, Winbox, SNMP, monitoring, and so on this VRF, increasing security, of course. And NAT, the same. NAT can be offloaded. We can offload with the connection tracking, also the NAT process. We can decide what to offload. MikroTik has a smart connection offload algorithm, so-called, that ensure that the connection with the most traffic are offloaded and the other are not. It depends on the capability of the router we use, if we have 2,000 or 4,000 connection offloaded. And starting from 7.18, also VXLAN can be offloaded. It's very, it's just the news, okay? Last week news. We can offload VXLAN, but VTAP are not supported on bonding and VLAN interfaces, so it's very tricky to work with MLAG with VXLAN at the same time, but who knows, maybe in the future we can use it. This is the configuration of the NAT in the hardware offloading. So we need another router, of course, because let's say PPPoE doesn't support offload. We can use another router, send the traffic to that router, configure the router this way, and have the NAT in the hardware. Please notice that the hardware offloading is disabled on the WAN port and in a way re-enabled only for established and related packet in the forward chain with the fast track connection action. And this is another screenshot of a working machine running layer 3 hardware offloading with NAT with some configuration over there. As you can see, this connection is in the hardware offloading. These are not in the hardware offloading. MikroTik decides for us. We have also quality of service in the hardware. Well, it's a very huge topic, and I have only 2 slides on it, but I want to, the only thing I want to tell is that we can use the hardware offloading quality of service starting from the 7.17 router S version, and we, with this configuration, with this feature, we can mark traffic in the hardware based the marking on VLANs or DSCP, on packets and so on, in the hardware, I mean, with the switch rules. We can also make some QoS enforcement. It's funny and it's amazing because one switch tells to the other, please send me less traffic, because there is a congestion on the network. So it's very nice to have this feature in switches. We have also active queue management with some well-known protocol, for example, random early detection, and priority flow control to create some bandwidth allocation and different priority for the traffic. It's a huge topic, I mean. So, let's go to conclusions. First of all, MLAG, in my point of view, is the key to obtain high availability and redundancy, but we need to configure precisely the VLANs, and the multiple spanning tree protocol must be enabled, in my opinion. Layer 3 hardware offloading, enhanced routing performance, of course. We need to careful design everything, and we need to select the right hardware. And in case we need to use a Cloud Core Router 2116, we can select what to offload and what not to. The NAT, the same, can be offloaded. We have 2,500 entries in the 2116 and 4,000 on the 2216. We can balance fast track and non-fast track traffic with firewall rules. Quality of service, the same, is very important, but it's crucial to evaluate and test. Each network is different to each other. VXLAN is another topic. It's the starting point to have EVPN on MikroTik. Could be a very change and next generation for MikroTik. Who knows? Let's see. But VTEP are not supporting the bonding interface and VLAN interfaces, so with MLAG it's very complex by now. And the final note. This would be my personal approach to data center configuration with only MikroTik devices. I know we can do with a lot of vendors, a lot of devices with, from other vendors, of course, but I would like to start a discussion about what MikroTik can do if we use only MikroTik. Why not? We can, okay? It's my point of view, and I want to let you know that this approach is not just theoretical, but it's battle tested. So I have a lot of customers with this kind of configuration. They are using this configuration to forward gigabit of traffic, and it works. It works very well. Okay, so this is my presentation. Thank you very much. Ho corso come un...
Thank you, Alessandro. Questions? Raise your hands. Don't be shy. No one? Oh.
Yeah.
When you said that VTEP is not supported on a bonded interface or VLAN interface, is it work differently on MikroTik? Because I always thought that VTEP it's usually loopback interface and then it doesn't matter.
I mean,
and the second follow-up question to this, why do you need unbonded interface? Because if you have VXLAN, you just do ACMP, like, so you don't need MLAG in the first place. You just do all layer 3 in the core. Thank you.
Thank you. Well, in this topology, I use MLAG as a core switch for all the network. So each router is connected through a bonded interface to the MLAG. That's why it's not possible to use layer 3 hardware offloading configuring the VLAN on the bonded interface. That's why you can't. If you configure the interface as it is, yes, of course, you can establish the VTEPs on that interface and offload the VLAN, the VXLAN. But if you want to run layer 3 hardware offloading, you cannot, because you have a bonding interface on the entrance interface. I answer your question. Okay. So that's why.
Other questions? Yeah.
Hi. A couple of questions. Firstly, you said when your upstream providers come into the network, you VLAN them individually. Do you mean you're tagging on ingress? Or do you ask that they're already tagged?
No, wholesale providers tag each customer in a separate VLAN.
I see. Yeah.
And encapsulate all these customer VLAN in a service VLAN. Then they give you a kit, a router, in which in a single port, they bring to you all the VLANs together. So you need to decapsulate each VLAN separately. That's why I make a tag stacking to add a new VLAN, the third one, drive all the VLANs to the, for example, to the PPPoE servers, the access concentrator, in which I configure only the service VLAN. And finally, I can use the PPPoE range VLAN to avoid configuring each customer VLAN on the access concentrator.
I understand. So that was from the access perspective.
Yeah, the access perspective.
On upstream to say a transit provider.
Oh, sorry.
Did your no, that answers both sides really. But did your design assume that some upstream providers, like a transit provider, will do lagging? And if so, what experience have you found?
Yes, I have some experience with lagging with the access provider, the upstream provider. For example, I work with Namex in Rome. They can provide you with 2 ports with lag, and both ports are active at the same time. The bandwidth is shared between the 2 ports, and in case you need to, let's say, upgrade one router, you can do it in real life, because the other router is acting as the master one.
That's good to know. You can ask for that. Cheers.
Thank you.
Other questions? It was a very technical presentation.
Yes.
No other questions? Nice. So everybody understood.
Thank you.
Thank you.